Hello, this is Mr. Bradley, and this lecture is intended to give you some background information and some understanding of kinematics in one dimension. Kinematics is basically the study of how things move in a straight line. You're talking about the physics that the early Greeks like Aristotle and Plato first kind of worked on. You know, the first questions that were asked about how things move and how things gain speed and how the distances that are traveled when things are moving. And this was the kind of physics that was done all the way up through the times of Galileo, really kind of culminating with the work of Newton. So, this is really like the beginning and the bulk of what we call classical mechanics in physics. When we're going to talk about the kinematics of motion, there are some things that, some terms that you have to understand, terms that are going to get thrown around a lot, especially the letters that go with them, and then the units of the things that, of these particular quantities. So let's start off here by just discussing the concept of time. Time will be represented by the letter t in equations. It's the lowercase t. You also might see this delta in here, which is, this triangle shape. That stands for change in time. That's a pretty common symbol that's used in math and in physics. And of course, time is really just, when we talk about time, we're really talking about how long it takes for something to happen. Maybe you're walking for 10 seconds or driving for 30 minutes or whatever. That would be the time, the change in time. There's lots of time units that we use. Seconds, hours, minutes are pretty common. And then the key thing here is that time is something we call a scalar quantity. Now, we're going to talk about vectors and scalars more later, but a scalar quantity is really something that has a number that describes it, a number that describes the magnitude or the size of the quantity, but there's no direction to it. We don't really say that time has a direction. Of course, we talk about being forward in time and backward in time because time moves on, but really time doesn't have a direction to it like some other things will that we'll see in a bit. Okay, another physical quantity that we discuss when we think about kinematics is the concept of distance or distance traveled. If you see the lowercase d in an equation, that is representing distance. And really what we mean by that is just the cumulative distance traveled by an object, how far you've gone total on a trip. So, that's like what an odometer in a car measures. There's a lot of distance measurements out there. Again, maybe meters, feet, miles. Those are all some basic units, and then some smaller and bigger units there, like centimeters, inches, kilometers, etc. Distance is also a scalar quantity. When we talk about the distance that you travel, there's really no direction to that. Now, there's another quantity that measures length per se, and that's called displacement. But displacement is really a lot different than distance. In kinematics, when you see the term delta x, or x minus x0, that really means displacement. That means what's the change in position of an object. That's really kind of what displacement is. By the way, I'm using the letter x here, but of course you could use the letter y as well. I'm using x because it's on a horizontal axis. If I was using y, that would be because I'd be talking about like a vertical axis. So when you see delta x, you're really talking about change in like horizontal position. Displacement is the distance between the initial and final position. So if you start in one place and end in another, it's the straight line distance from start to finish. It's also measured in meters, feet, miles, etc. But the trick here is that displacement is a vector quantity. As we do some examples in here, you'll see what I'm talking about with that. But really, the big difference between distance and displacement is distance is like a cumulative distance traveled. Displacement takes into account all the changes in direction that you might make along the way. Okay, so the previous quantities that we discussed are used to calculate some things. The things that I talked about on the other page are really basic things that you can measure. You can measure distance, you can measure displacement, you can measure time. Everything that comes after that are typically things that are calculated. Now, we might have a tool that will measure, say, velocity, but really what it's doing is it's measuring distances and calculating velocity for you. So, don't let yourself get fooled into thinking that there's a tool that actually measures speed. What there is there's a tool that measures distances in very short periods of time and then calculates the velocity from that. So there are two things we want to talk about here. There's something that we would call average speed or average velocity. Now, I use the different colors here on purpose. Average speed is a scalar quantity, okay? Average velocity is a vector quantity. So both of them are represented with the symbol v with a line on top of it. This straight line on top of it with no arrow is meant to show you like average. So this is average speed or average velocity. And it's really the average distance that is covered, the average rate that distance is covered over long distances, or the average displacement that is covered over long distances. If I use distance, I calculate speed. If I use displacement, I calculate velocity. This is a scalar quantity. Average velocity is a vector quantity. It's measured in feet per second, meters per second, miles per hour, kilometers per hour, etc. This is the distance or displacement quantity. This is the time quantity on the bottom. Remember, hopefully from math class, that a rate is really a change in anything over time. That's one thing that's really important to remember. So whenever you hear the term rate, you know you're going to be dividing by time like we do here. Now, there's also something that we would call an instantaneous speed or instantaneous velocity. This is really like how fast you're going at a moment, if you will. This would be represented by v or v sub naught in an equation. This means final velocity, this means initial velocity, as we'll come back to in just a little bit. Really, it's the same as an average speed, which is the distance over time that's covered, but now we're talking about a very small time here. Instead of talking about how far did you go in an hour to calculate average speed, I might say how far did you go in, a tenth of a millisecond. You're going to be taking a very small distance over a very small time, and then that really gives you an idea of how fast you were going at a moment in time. This is what a speedometer or radar gun displays. And again, remember I said, this is something that's calculated by the device that you're using to measure that. Now, the equations that I would use to calculate these things are given to you right here. Now, this is kind of weird language, so let me describe to you what you're looking at. This is saying that the average speed of an object is the distance that's covered divided by the time it takes to cover that distance over a big interval. This is saying that the average velocity of an object is the displacement of an object over the time that it takes to cover that. And again, I was pretty intentional here with my colors. Anything that you see here in blue is a scalar quantity. Anything you see in red is a vector quantity. This equation down here is telling me how to calculate instantaneous velocity. And this terminology is something that you'll be introduced to when you take a calculus course. But really notice that it's the same equation that I have up here for average velocity, except now I'm saying imagine that the time I'm using in the denominator gets very close to zero. This is just another way of saying I'm looking at the displacement over the time interval when the time interval gets very, very, very small. That's what this terminology is showing. Okay, so now that we know a little bit about distance and position and speed and velocity, now we can talk some about acceleration. Acceleration is really the concept that things either speed up or slow down, although we'll find out later that it also has to do with the concept that when things change direction, they accelerate as well. But acceleration in an equation is represented by the letter A, and by definition it's the rate of velocity change. So of course remember that when you find a rate, you divide by time. So if I was going to try to calculate acceleration mainly, I would take the change in velocity divided by time. This is final velocity minus initial velocity divided by the time it takes to make that change. And that's really the definition of acceleration. The units of acceleration are pretty interesting because you have two time units in there, and this really gives people a lot of trouble sometimes. If you were going to take speed in meters per second and divide by time in seconds, you'd have meters per second per second. Notice I have a comma here. That's intentional to make you pause a little bit. You say, the acceleration of something might be 10 meters per second, meaning that it is gaining speed. It's gaining 10 meters per second of speed every second of time, getting 10 meters per second faster every second. Because you have two seconds, if you will, in the denominator, two of the same time units, sometimes people want to be cute and they want to combine them together, and so they might say meters per second squared. And that's a way that you see it typed sometimes. I frankly don't really prefer that. I prefer it like this up here, meters per second, but just don't be surprised if you see that. Now, the common unit of acceleration that you would see in the English system, especially in the United States, regarding cars, would be miles per hour per second, because we describe how fast things go in miles per hour, and then we would talk about that speed changing every second. And so you might say that a car accelerates at a rate of, 7 miles per hour per second, meaning every second it gets 7 miles per hour faster. So those are two common acceleration units you might see. But for sure there's other ones out there. All right, well, when we take those 4 quantities that I just discussed with you, position, time, velocity, and acceleration, you can relate those things together with these equations, these 4 equations. These are really, really 4 pretty common equations that you're going to use a lot of, and these are the results of hundreds of years of studying physics. To find out like how acceleration depends on change in position, and how velocity and position depend on time, and all these things, and these are really the 4 cleanest ways of looking at those comparisons. So these are the main kinematics equations, and you're going to get a lot of practice using these kinematics equations. This equation is the one that relates acceleration, initial velocity, final velocity, and time. This is the equation that relates acceleration, initial velocity, final velocity, and position, or displacement. This one relates displacement, initial velocity, time, acceleration, and time. This one is just a simple way of calculating average speed. One thing that's really important with this 4th equation is that this equation works if things are undergoing uniform acceleration, constant acceleration. But I mean, like this note here says, these equations allow you to predict a result based on the physical relationship between variables. These equations themselves are not physical laws. What I mean by that is, you're never allowed to say that, something happens because of this equation. That's not a because. This is just a way of describing what happens. There are other reasons behind the because, and those are the reasons that we'll get into. It's a big part of what I'm going to want you to understand over the course of the next couple months. All right, well, when you use those kinematics equations in problems to solve for unknown variables, there's a really important process that I really want you to go through. Okay, that process, sometimes this process might seem a little bit lengthy, but it's something that you really need to go through every time. I kind of equate this to an athlete sort of going through the exact same progression in their athletic endeavor, whether you're a swimmer who really concentrates on doing the exact same stroke every time, or whether you're a sprinter that really concentrates on stepping out every time you're putting one foot out in front of the other, or whether you're a football player that goes through the exact same sequence of practice every time. This is the same thing you have to do when you're solving problems. The faster you can get at this, and the more you can streamline it, the better. But you really have to start off first by going through it. So, I just want to mention here that when you're solving problems in physics, the very first step to doing that is just identifying what's already been given to you. When you read through a problem, what information has been given to you? Those are called the givens. You identify those and you write them down. Okay. Then you try to figure out, what is it that I'm trying to solve for? What's the unknown? You write that down. When you write those things down, you want to write down the number as well as the units that are given to you. And then also, if you need to, draw a sketch of the situation. I mean, pictures are so useful in physics, especially in kinematics. Having a little picture showing the direction that things are moving and which way they're accelerating and all of that really, really is very useful. Step number 4 here is really pretty important as well. Okay, this is step number 4. Check the units to see if they agree. If the units are not in agreement, you're going to have to convert units. The kinematics equations that I showed you on the previous slide do not work if you don't have agreeable distance units, velocity units, time units, acceleration units. They just don't work. You get answers, but the answers are nonsensical. So that means if you have miles per hour and as your velocity, and you have meters per second as an acceleration, you've got to change one of those so that the distance units and the time units agree. Then what you do is you go to the list of kinematics equations and you figure out which equation is the best one to use given what I have and what I'm looking for. You'll probably have to rearrange the equation. I think it's a good idea to go ahead and rearrange the equation first What I mean by that is, if I'm looking at the kinematics equation, acceleration is velocity squared minus initial velocity squared divided by 2 times the displacement. And if I'm actually trying to solve for the displacement, I actually think it's a better idea to rearrange this equation first. I know some people like to substitute numbers in where they go and then solve for the unknown, and that's okay, but that means you have to solve the equation every single time. If you rearrange this equation first, then you now have given yourself another equation that you can use in that same situation later. And I don't know, also, I just tell you that the more you rearrange equations, the more you sort of memorize them. And so you'll be able to know all the different forms of this equation kind of in your head because you've rearranged it so many times. That's just a tip that I think is pretty valuable. So you might need to rearrange the equation, and then you go ahead and substitute what you have into the equation with the units. This is another thing that's super important. Okay, you need to, especially on your paper, you need to write down what the units were in the equation. You're doing that so that you can make sure that units cancel out and that you're ending up with what you expect to end up with. Finally, you solve for the unknown, and then you report your answers with the appropriate number of significant figures. Significant figures are the way that we communicate how accurate and precise the final answer is. There's a whole other discussion and video on sig figs that I'll provide for you. Guys, here's the key thing when you're solving problems. You are not just finding the answer, you're showing the solution. Finding the answer is one thing, but you're trying to show me that you understand how to solve these problems. You're showing the process by which the solution is found. That is what problem solving in physics is about. If you want to find the answer, that's pretty easy. You can look up answers, you can look at answers in the back of the book. You have a solutions manual available to you that has the answer in it. If you want to find the answer, just go look up the answer. I want you to show that you can figure out the solution. Okay, so now that we have looked at the kinematics equations and talked about the problem-solving process, let's just work through an example of how we would do all of this. So I picked example 2.6 out of your book. It's on page 27. The problem, I'll go ahead and read it. It says, you are designing an airport for small planes. One kind of airplane that might use this airfield must reach a speed before takeoff of at least 27.8 meters per second. That's about 100 kilometers per hour. And it can accelerate at a rate of 2.00 meters per second. The runway is 150 meters long. Can this airplane reach the required speed for takeoff? If not, what minimum length must the runway have? Well, here's how I'm going to approach this problem. I'm going to first of all start off by just writing down what I know. So I know that an airplane is going to start from rest, so the initial velocity is 0. I also know that it's going to have to reach a speed of 27.8 meters per second, so the final velocity is 27.8 meters per second. I know that its acceleration is 2.00 meters per second. What I'm trying to find out is, can this happen within a displacement of 150 meters? Well, the simplest thing to do here is just go ahead and solve for the displacement in this situation. That's really the simplest thing to do. Then, if the displacement is less than 150 meters, you know I'm going to make it. If it's not, if it's more than 150 meters, you know I'm not going to make it. So, I'm going to go ahead and look for the kinematics equation that will help me solve this. First of all, I'm going to do a quick check here. Are my units going to all work out with each other? Yeah, sure enough, this is meters, seconds, seconds. If my velocity had been only given to me in kilometers per hour, I would have needed to convert that to meters per second. But since it was given to me in meters per second, I'm good to go. So I don't need to worry about converting any units. I can go ahead and just pick out the right kinematics equations, and I'll be good to go. Well, I'm going to look at the kinematics equation from the previous page. That is this one right here. Okay, that's the kinematics equation that I'm going to use. It's not rearranged for displacement right now, but it has all the variables in it. I'm relating acceleration, final velocity, initial velocity, and displacement. So the kinematics equation that I'm going to use is that acceleration is equal to final velocity squared minus initial velocity squared divided by 2 times the displacement. Alright, well, when I rearrange that equation for displacement, I need to really isolate this on one side all by itself with everything else on the other side. Because that's in the denominator, of a fraction, I need to multiply by that on the other side, and then I'm going to divide back by acceleration. In essential, I'm just going to switch those two things places. The displacement of the airplane is the final velocity minus the initial velocity, both of those squared, divided by 2 times the acceleration. That would be the equation that I'm going to use to solve this problem. All right, well, I need to give myself some more room down here so that I can write this. I'm going to solve for displacement by using the final velocity squared, so 27.8 meters per second squared, minus the initial velocity squared, which is 0, that's nice, divided by 2 times the acceleration. The acceleration is 2.00 meters per second. Okay? When I evaluate this on my calculator, I get 772.84, and then this is meters squared per second squared. Both the meters and seconds get squared as well. Divided by 2 times 2 is 4 meters per second. And when I continue to evaluate this, I get 193.21. Well, and then let's talk about the units. This meters cancels out one of those meters. This seconds cancels out one of the seconds, and that seconds cancels out the other seconds. And so really I'm just left with meters, which is good because I was trying to find a displacement. Displacements are measured in meters. That's a good thing. So according to this calculation, this runway needs to be 193.21 meters long. Well, this number right here is ridiculously precise. I mean, 193.21, that's got 5 sig figs. My original numbers did not have 5 sig figs. My final velocity only had 3, and my acceleration only had 3 sig figs, which means my answer also can only have 3 sig figs. And so 193.21 just becomes 193 meters. Since the 0.21 is less than 0.5, that rounds down, and so I'm just left with 193 meters. Okay, so the answer to my question is no. It's not going to make it on a 150-meter long runway because it needs 193 meters to take off. This is really what I would expect all of your physics problems to look like. Okay, you're showing me your givens. You're showing me the equation you're going to use. If you go ahead and just have it rearranged right away, I'm okay with that. And then you show me the equation with the numbers and the units substituted in, solved out with the final answer boxed off with the right number of sig figs. Okay, well, I hope this video has helped you out. I hope it gives you a nice review or refresher for what you need in this class. Good luck solving problems with kinematics. Have a great day.